David, the last time we spoke, it was for an introductory episode on the measurement problem. And as we both know, it was extraordinarily well received. I'd wanted to start that one with some historical context, but at your suggestion, we went in a different direction. And that was, of course, the right move. So I thought in beginning this episode about another pedagogical episode, this time about the direction of time, I ought to just leave it to you about how you thought we best ought to start it.
Okay. I mean, let me start out by setting up what the problem is. There's a certain tension between what modern physics, by modern physics I mean physics since Galileo and Newton, what modern physics seems to be telling us about the fundamental structure of the world and various characteristics of our everyday macroscopic experience of being in the world. There's a deep tension between those two things vis-a-vis the question of the difference between the past and the future. And let me say a little bit about how that tension comes up. Suppose that you're shown a film of two billiard balls colliding somewhere in intergalactic space. So the only thing you see in the frame are these two billiard balls. So the film looks like this. You've got initially a billiard ball sitting motionless in the center of the frame. Another billiard ball comes in, knocks into it, stops, and the first billiard ball goes off and exits the frame on the other side. Good. Imagine that you were shown, or let's put it this way. Suppose you were shown such a film and asked to guess whether you were being shown the film forwards or in reverse, okay? Imagine being shown the film I just described in reverse. You'd see something like this, okay? And what it's important to note is that this is every bit as much in accord with everything you think you know about collisions between billiard balls as this is, okay? So that if you were shown such a film and asked to guess whether you were being shown the film forwards or in reverse, nothing that you know about the way billiard balls behave is going to give you any help in making the correct guess, okay? Because it seems to be a feature of whatever laws it is that govern collisions between billiard balls, that given any collision between two billiard balls, given a sort of account, a film of any collision between two billiard balls, the exact same sequence of events running in reverse is going to be just as much in accord with everything you know about the way billiard balls behave when they collide as the film running forwards. Good. Physicists summarize this situation by saying that the laws that govern collisions between billiard balls are time reversal symmetric, or are invariant under time reversal. And what that means is that for any process that's in accord with those laws, like this one, the process going exactly in reverse, the backwards process, is also in accord with those laws, and just as much in accord with those laws as the forward-going process is. Good. It happens that this is not merely a feature of the laws governing collisions between a pair of billiard balls. It turns out to be breathtakingly more general than that. It governs, first of all, collisions between any number of billiard balls. And as a matter of fact, this feature of time reversal symmetry, or of invariance under time reversal, is a mathematical feature of every single one of the proposals for a fundamental physical theory that anybody has taken seriously since Newton. Okay, I mean, this is actually maybe worth pausing over for a minute. This is an astonishing fact. You know, our picture of the fundamental structure of the physical world has changed in revolutionary ways, has changed in earth-shaking ways a number of times since Newton. The revolution of quantum mechanics, the revolution of relativity theory, the discovery of fields in the 19th century, right up to very contemporary talk about string theory and so on and so forth. Vast things about what we thought about the fundamental structure of the physical world have changed. Questions of determinism, questions about whether there's even invariably a fact of the matter about where a billiard ball is located or something like that. One thing that has survived all of these revolutions is that all of our serious proposals for a fundamental universal theory of the world have always turned out to be time reversal symmetric. You might say that if somebody woke you up in the middle of the night and asked you what is the most consistent lesson of all of our experience with theoretical physics from Galileo up to now, what's the one thing that has survived all these revolutionary changes? The claim that the fundamental laws of physics are invariant under time reversal. Good. So, judging from the fundamental laws of physics, we take ourselves to have very good reasons to believe that anything that can happen can also happen exactly backwards, okay? And that given anything that can happen, given anything that's in accord with the laws, that thing happening exactly backwards is exactly as much in accord with the laws as the thing happening forwards. Good. So this is one end of the tension, okay? These very compelling reasons we have to believe from our experience with fundamental physics, with the physics that governs the microscopic constituents of the world, that we have time reversal symmetry, that anything that can happen can just as easily happen backward.